Unions and intersections. The union of the sets A and B is the set of elements that are in A or B or both. We use a U-shaped symbol to indicate the union. So we have the union of A and B is the set of X such that X is in A or X is in B. Here's a Venn diagram illustrating the union of sets A and B. Notice how both sets A and B are completely shaded for this Venn diagram. The intersection of A and B is the set of elements that are simultaneously in A and B. We use an upside down U-shaped symbol for the intersection. So we have the intersection of A and B is equal to the set of X such that X is in A and X is in B. Here's a Venn diagram illustrating the intersection of sets A and B. Notice that the only part shaded is the part that's common to both A and B. Let's look at an example. Let A be the set consisting of the numbers 0, 1, 2, 3, and 4, and we'll let B be the set consisting of 3, 4, 5, and 6. Evaluate the union of A and B and the intersection of A and B. Well, the union of A and B is the set consisting of 0, 1, 2, 3, 4, 5, and 6. Notice how it consists of elements that are in A or in B or in both. The intersection of A and B consists of just the numbers 3 and 4. These are the numbers common to both sets A and B. Here's a Venn diagram giving a nice illustration of this example. Notice how 3 and 4 are in the intersection of A and B. The other elements from A, 0, 1, and 2, are shown inside the set A but outside of the intersection. And similarly, 5 and 6, which are in the set B, are outside of the intersection of A and B. Let's look at another example. Let N be the set of natural numbers, and let Z be the set of integers. Evaluate the union of N and Z and the intersection of N and Z. Well, the union of N and Z is just Z, and the intersection of N and Z is just N. Note here that N, the set of natural numbers, is a subset of Z, the set of integers. In fact, whenever A and B are sets and B is a subset of A, then the union of A and B is equal to A, and the intersection of A and B is equal to B. That's exactly what happened in this example. One more example. Let E be the set of even natural numbers, and let O be the set of odd natural numbers. Evaluate the union of E and O and the intersection of E and O. Well, the union of E and O is N, the set of natural numbers. The intersection of E and O is the empty set. In general, we say that sets A and B are disjoint or mutually exclusive if the intersection of A and B is empty. That's what happened here. E, the set of even natural numbers, and O, the set of odd natural numbers, have no elements in common. They are disjoint or mutually exclusive sets. Their intersection is empty. Here's a Venn diagram illustrating what it looks like when two sets are disjoint or mutually exclusive. Let's prove a theorem about the union of two sets. If A and B are sets, then A is a subset of the union of A and B. Let's just look at the diagram for the union of A and B, just to make sure that we believe this theorem. We could see here that A does in fact look like it's a subset of the union of A and B. Okay, let's start writing the proof. Suppose that A and B are sets and let X be an A. That's our opening statement. Again, the opening statement, we write down what we're given and we fix any arbitrary but specific elements. Here we're fixing an X in the set A. Before we go on, recall that if P is a true statement, then the statement P or Q is true no matter what the truth value of Q is. We're going to apply that in this proof. We're going to let P be the statement X in A and Q the statement X in B. Since X in A is a true statement, so is the statement X in A or X in B. And we'll put this into the proof. So since X in A is a true statement, it follows that we have X in A or X in B. So why did we want to do that? Because the definition of the union of A and B is the set of X such that X is in A or X is in B. So the element X now satisfies exactly what we need for it to be in the union. So therefore, X is in the union of A and B. Since X was an arbitrary element of A, we have shown that every element of A is an element of the union of A and B. That is, we have shown for all X, X in A implies X in the union of A and B is true. Therefore, A is a subset of the union of A and B. Let's do one more theorem. B is a subset of A if and only if the union of A and B is equal to A. Before we begin the proof, let's look at a technical note that will help us to prove this. Let X and Y be sets. The axiom of extensionality says that X and Y are the same set if and only if X and Y have precisely the same elements. In other words, X is equal to Y if and only if, for all X, X is in X if and only if X is in Y. The statement, for all X, X in X if and only if X in Y, is logically equivalent to the statement, for all X, X in X implies X in Y, and for all X, X in Y implies X in X. So, X is equal to Y if and only if, for all X, X in X implies X in Y, and for all X, X in Y implies X in X. In other words, to show that the set X is equal to the set Y, we can instead show that X is a subset of Y and Y is a subset of X. We'll be applying that in this theorem when showing that the union of A and B is equal to A. Instead, we could just show that each of those is a subset of the other one. Okay, we're ready to begin the proof. There are two directions for this proof because it's an if and only if. So we'll start by going to the right. In other words, we're going to assume that B is a subset of A and use that to prove that the union of A and B is equal to A. So starting with our opening statement, suppose that B is a subset of A. Now remember, by the technical note that we just talked about, we're going to do two subset proofs instead of a single equality proof. So we'll start by showing that the union of A and B is a subset of A. So we'll let X be in the union of A and B. Then by definition of the union, X is in A or X is in B. If X is in A, then X is in A, of course, trivially. If X is in B, then since B is a subset of A, that's what we're assuming, it follows that X is in A. Since X was an arbitrary element of the union of A and B, we have shown that every element of the union of A and B is an element of A. That is, for all X, X in the union of A and B implies X in A is true. Therefore, the union of A and B is a subset of A. And now the other direction. We're going to show that A is a subset of the union of A and B. But we already know this. We proved this in the last theorem. So by theorem 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, 2.4, Since the union of A and B is a subset of A, and A is a subset of the union of A and B, it follows that the union of A and B is equal to A. Okay, so we successfully proved the direction going from left to right. Now we do the other direction, from right to left. In other words, we're going to assume that the union of A and B is equal to A and use that to prove that B is a subset of A. So now suppose that the union of A and B is equal to A, and let X be in B. Since X is in B, it follows that X is in A or X is in B. We're using that same logical trick that we used in the proof of the last theorem. Therefore, X is in A union B. That's by the definition of the union. Since the union of A and B is equal to A, we have that X is also in A. Since X was an arbitrary element of B, we have shown that every element of B is an element of A. That is, for all X, X in B implies X is in A. Therefore, B is a subset of A. And we've done it.